Okay, welcome to this video. This is the feedback on all the questions of the CGP White Book on magnetism. I'm going to try and do it in less than 15 minutes. I'll attack. So, let's begin. Complete the sentence using one of the words below. Magnetic force is an example of a non-contact force. Okay, your magnet does not have to touch the magnetic object to attract it. Define the term magnetic field. So the magnetic field is an area around a magnet where magnetic object will undergo a force or will experience a force. Name two magnetic materials. So you have the choice. There are three elements: iron, nickel, and cobalt. You could add steel, which is a what's the word I'm looking for? Sorry. It's made of iron and other stuff. An alloy made of iron and other stuff. Next one, figure 1, show a bar magnet. Draw the magnetic field lines onto the diagram in figure 1. So again, you don't have to draw too many, but make sure that they're going from north to south. Make sure all your arrows are in the right direction. Okay. Which of the following statements are correct for magnets? Like poles attract each other? Absolutely not. The magnetic field at the north pole of a magnet is always stronger than at the south pole? Absolutely not. The closer together the magnetic field line, the stronger the magnetic field. This is correct. The higher density of magnetic field line, the stronger the magnetic field. So that one is true. Magnetic field lines point from the north pole to the south pole of a magnet. That is also true. The force between a magnet and a magnetic material can be attractive or repulsive. This is false. A magnet will always attract a magnetic object. So 3 and 4 were correct. A block of cobalt is held in place near the bar magnet shown in figure 2. A steel paperclip is placed against the block of cobalt at point P shown on figure 2. The paperclip sticks to the block of cobalt. State why this is the case. The block of cobalt becomes an induced magnet when it is placed in the magnetic field of the bar magnet. All the domains are going to align. That's because the force of attraction between the paperclip and the cobalt that is going to be stuck to it. The bar magnet is removed. Explain what happens to the paperclip. Over time, the block of cobalt will demagnetize. All the domains are going to start being random again, so the paperclip will become unstuck and fall. The student wants to investigate the magnetic field of a horseshoe magnet, shown in figure 3. Explain how a compass could be used to determine the magnetic field of a magnet. So the needle of the compass points in the direction of the magnetic field it is in. If you put the magnet on a sheet of paper and move the compass along the field lines of the magnet, and marking the direction of the compass needles at each point, join up the mark to create a diagram of the magnetic field lines. State what would happen to the compass if you were to move it far away from any magnets. Explain why this would happen. So if it's far away from the magnet, it will not undergo the magnetic field of those particular magnet, so it is going to align with the magnetic field of the Earth and point towards the North Pole, or the geographic North Pole, because it's aligning itself with the magnetic field of the Earth. Electromagnetism. Figure 1 shows a wire which has a current flowing through it. The current is going from right to left. The flow of charge creates a magnetic field around the wire. On figure 1, draw a field line showing the direction of the magnetic field created. So remember, you're going to create a magnetic field which are circles around the wire, and you're going to use the right-hand rule to determine the direction of the magnetic field. Okay, and you should have something like this. If you do it really well, the line should be way close to the wire than they are further away. The direction of the current is reversed. What effect does it have on the magnetic field? It will also reverse the magnetic field. State one way in which the magnetic field strength around the wire would be increased. You could increase the current. If you increase the current, you increase the magnetic field around the wire. A current-carrying solenoid has a magnetic field outside it similar to a bar magnet. State one way in which the magnetic field strength of a solenoid can be increased. Remember the 3 C's. More current, add a core, add more coil. Easy. The north pole of a magnet is brought near to the current-carrying solenoid as shown in figure 2. State whether the north pole is attracted or repelled by the solenoid. So in this particular scenario, it is repelled because the direction of the current means that the left hand of the solenoid act as a north pole. Okay, and like pole repels, therefore they're going to repel each other. If the current was going in the other direction, then the part facing the north pole here would be the south pole. They would attract each other. The motor effect, so that is the force applied. That's the left-hand rule. It's the force applied to a wire when a current is applied to it into a magnetic field. So a 0.75 meter section of wire carrying a current is placed into a magnetic field. When a wire is perpendicular to the field, it experiences a force of 1.2 newtons. So we have a force, we have a current, we have the length of the wire. We have to calculate the magnetic flux density. So the equation F equal B times I times L. We know F is 1.2 Newton in the right unit. We don't have to convert it. The current is 0.4 amps. We don't have to convert it. And the length of the wire is 0.75 meters. It's in the right unit. We don't have to convert it. Fine tune. We are going to make B the subject of the equation by dividing 1.2 by 0.4 times 0.75. And this is a magnetic flux density of 4 Tesla. It's pretty huge. A student carries out an experiment using a horseshoe magnet and an iron bar connecting in a circuit. Part of the setup is shown in figure 1. The student rotates the iron bar 90 degree clockwise and measures the force acting on the bar as she does so. She then plots her results on a graph of force F against angle of rotation. So the wire is going to undergo the most force when it is perpendicular to the magnetic field. Okay, so at 90 degree, or in that case at 0 degree, it will be maximum, and then it's going to decrease when you're increasing the angle. And when the wire is perpendicular, or in that case parallel to the magnetic field line, there will be no force at all. So A was the correct representation. A wire is placed between two magnets as shown in figure 1. A current is flowing through the wire in the direction shown. What will happen to the wire? So A, it will move. Then you're going to have to use the left-hand rule. The magnetic field, so remember FBI on your left hand, the thumb is the direction of the force, the index is the direction of the magnetic field north to south, so pointing to the left, and the current is going upwards. Therefore, the force is applied towards you out of the paper. Figure 2 shows a part of a basic DC motor. A coil of wire is positioned between two magnetic poles and allowed to rotate. State the direction in which the coil will turn. So again, you're going to apply the left-hand rule to both wires. So let's tie to the one on the right-hand side, okay? So the current is going away from you. That's your middle finger going away from you. The magnetic field line is going from north to south. So it's going from left to right. The force applied is going down. That's going to be the opposite for the other half of the wire. So the motor is going to turn clockwise. Okay, the right part goes down, the left part goes up. It's going clockwise. Explain why the coil turns. The interacting magnetic fields of the coil and the magnets cause a force on each arm of the coil in the opposite direction, which causes the coil to rotate. Explain how a DC current can be used to make the coil, so a direct current can be used to make the coil in figure 2 continue to rotate in the same direction. And that's when you have to talk about the split ring commutator, which is going to switch the direction of current every half turn, making sure that it's always turning in the right direction. Okay, so swap the contact every half turn using a split ring commutator to reverse the direction of the current. This swaps the direction of the forces for each arm and keeps the direction of rotation constant. Okay, this is it. 9 minutes, easy. All right, keep on revising hard. Keep on practicing. Let me know if you need more practice. Let your teacher know if you need more practice. In the meantime, stay amazing. Keep on trying hard, and good luck with all your revision. Bye, guys. Take care.